In the previous lecture, you explored artificial intelligence, red teaming, and adversarial testing, where you challenge systems before attackers do and generate evidence of resilience. Now, you are moving into the reality that every enterprise eventually faces. What happens after deployment? A model that is safe and effective today may become unsafe or unreliable tomorrow. That is why runtime monitoring and drift detection matter. In this session, you will learn how to think about continuous artificial intelligence security through monitoring, drift detection, output anomaly detection, and behavioral monitoring. You will also see how tools such as Evidently Artificial Intelligence, Azure Machine Learning Monitoring, and Vertex Artificial Intelligence Monitoring support an enterprise assurance program. Before diving into drift concepts, let us establish why runtime matters more for artificial intelligence than for traditional systems. Traditional software systems generally behave consistently unless code or configuration changes. When you patch or update software, you understand what changed. Artificial intelligence systems can change behavior even when you do not change code. They can drift because the world changes. They can drift because data patterns shift. They can drift because users interact in unexpected ways. They can drift because new adversarial behavior emerges. This means that deployment is not the end of security. Deployment is the beginning of continuous assurance. As a leader or architect, you must design monitoring as a first-class architectural layer, not as a secondary operational feature. Now that you understand why runtime matters, let us define drift and why it matters for security. Drift occurs when the relationship between input and output changes over time. In some cases, drift is natural. Markets change. Customer behavior changes. Sensor patterns change. In other cases, drift signals risk. It may indicate data pipeline problems, biased behavior emerging, or adversarial manipulation. If you do not detect drift, you will not know when your model has silently become less reliable, less fair, or more vulnerable. Drift is not only a performance problem, it is an assurance problem. It affects trust, it affects compliance, it affects operational safety. Now let us focus on the first category, model drift. Model drift occurs when a model's performance degrades over time because the real-world data distribution no longer matches the conditions under which it was trained. For example, imagine a fraud detection model trained on transaction behavior from the previous year. New fraud patterns emerge. Attackers adapt. Customer purchasing behavior changes. If the model is not updated or monitored, it may miss fraud and generate false confidence. From a security perspective, model drift can increase exposure. A degraded model may allow adversaries to bypass detection. A degraded model may produce decisions that violate risk appetite. A degraded model may generate inaccurate recommendations that influence business outcomes. Model drift must be monitored through measurable performance signals. You must treat these signals as security telemetry, not merely data science metrics. Now that you understand model drift, let us examine concept drift, which is often more subtle. Concept drift occurs when the meaning of the target outcome changes over time. For example, consider a model designed to predict customer churn. The definition of churn may change due to new subscription models, pricing changes, or product strategy. If the underlying concept shifts, model predictions become misaligned with business reality. In security context, concept drift can affect what you classify as risk. A risk scoring model may become misaligned if threat patterns change or business tolerance changes. A content safety model may become misaligned if policy definitions evolve. Concept drift is particularly important for governance and compliance. If your artificial intelligence system supports regulated decisions, you must ensure its output remains aligned with the current concept definition, not a historical one. Architecturally, concept drift requires coordination between business owners, governance teams, and technical teams. It cannot be solved by retraining alone without confirming that the target definition remains valid. Now, let us move to a runtime risk that is highly relevant for generative artificial intelligence systems: output anomalies. Output anomalies occur when the system produces responses that are unexpected, unsafe, or inconsistent with policy. Examples include a customer service assistant suddenly generating aggressive or inappropriate responses, a compliance assistant generating misleading legal guidance, a large language model assistant revealing sensitive information due to subtle prompt patterns, an internal assistant producing hallucinated instructions that appear authoritative. Output anomalies may be caused by drift, but they may also be triggered by adversarial probing, retrieval manipulation, or context construction failures. This is why output monitoring is essential. You should monitor for spikes in safety policy violations, sudden increases in sensitive data exposure attempts, unexpected changes in tone, content category, or refusal behavior, repeated patterns indicating systematic exploitation. For leaders, output anomaly monitoring becomes an enterprise risk signal. It provides early warning before reputational damage occurs. Now that you understand outputs, let us discuss behavioral monitoring, which focuses on how users and systems interact with artificial intelligence. Behavioral monitoring examines patterns such as unusual volumes of requests from a single identity, repeated attempts to extract restricted information, prompt patterns consistent with jailbreak attempts, repeated queries that resemble model extraction behavior, tool usage patterns that exceed normal workflows. Behavioral monitoring is critical because many artificial intelligence attacks do not look like traditional cyber attacks. They look like conversation. They look like normal usage until you analyze patterns at scale. Architecturally, behavioral monitoring must integrate with identity and access systems, logging platforms, and governance dashboards. This is where security operations meets artificial intelligence operations. Now that you have explored drift and monitoring categories, let us turn this into a structured enterprise loop. A continuous artificial intelligence security loop includes collecting telemetry from inputs, outputs, and user behavior, detecting drift signals and anomaly patterns, investigating root causes using audit trails and context logs, applying remediation such as updating retrieval controls, adjusting guardrails, retraining models, or restricting access, validating improvements through evaluation and adversarial testing, reporting outcomes to governance and leadership. This loop ensures that security is not episodic. It becomes continuous assurance. For architects, this loop is not merely an operational practice. It must be designed into the system. If you do not design for observability, you cannot monitor effectively. Now that you understand the monitoring architecture, let us connect it to tools that support enterprise implementation. Evidently, artificial intelligence provides monitoring capabilities for machine learning models, including drift detection and performance tracking. It helps you detect when input data distributions change and when model behavior shifts. Azure Machine Learning Monitoring provides integrated observability for models deployed within Azure Machine Learning environments. It enables performance monitoring, data drift detection, and alerting aligned with enterprise cloud governance. Vertex Artificial Intelligence Monitoring provides similar capabilities for models deployed within Google Cloud environments, supporting drift detection, anomaly monitoring, and operational telemetry integration. These tools are enablers, not replacements for architecture. Your role as an architect is to define what signals matter, what thresholds trigger investigation, what alerts are routed to operations teams, how evidence is stored for audit, how governance reporting is generated, tools support execution, architecture defines intent and assurance. Now, let us ground continuous monitoring in a practical enterprise scenario. Imagine your organization deploys a large language model assistant for internal information retrieval. It accesses human resources policies, security guidance, and operational procedures. At launch, the system behaves correctly. Over time, employees begin using it more broadly. Some users probe boundaries. New documents enter the knowledge base. The assistant's outputs begin to drip subtly. It starts giving inconsistent guidance on security procedures. It occasionally includes outdated policy statements. It begins to answer questions that should be restricted. Without monitoring, this problem grows silently until an incident occurs. With monitoring, you detect output anomalies early. You investigate which documents were retrieved. You discover that outdated documents are dominating retrieval results. You adjust trust scoring and ingestion validation. You restore reliability before damage occurs. This is the value of runtime assurance. It turns silent failure into visible signals. Now that you understand the operational reality, let us elevate this to leadership thinking. Governance and compliance increasingly demand evidence, not claims. Continuous monitoring generates evidence. Drift dashboards, anomaly logs, audit trails, and remediation records demonstrate active risk management. For leaders, this evidence supports regulatory readiness, executive assurance, customer trust, operational resilience. If you cannot monitor, you cannot prove control. If you can monitor, you can demonstrate maturity. This is why monitoring is not only technical, it is a strategic governance capability. Now that you have explored monitoring, drift, anomaly detection, and continuous security loops, let us summarize the most important insights you should carry forward. Runtime matters because artificial intelligence systems can change behavior even without code changes. Model drift degrades performance and can increase security exposure. Concept drift changes the meaning of outcomes and can misalign systems with governance expectations. Output anomalies can signal safety failures, data leakage risk, or adversarial exploitation. Behavioral monitoring detects abuse patterns that look like normal usage at small scale. A continuous artificial intelligence security loop integrates monitoring, investigation, remediation, validation, and reporting. Tools such as Evidently Artificial Intelligence, Azure Machine Learning Monitoring, and Vertex Artificial Intelligence Monitoring support implementation, but architecture defines signals, thresholds, and governance reporting. Continuous monitoring produces evidence that strengthens compliance and executive assurance. Now that you understand why continuous monitoring and drift detection are essential for secure artificial intelligence systems, reflect on your organization. Do you monitor model behavior after deployment or only before launch? Do you detect drift and anomalies early or only after incidents occur? Do leaders receive continuous assurance evidence or periodic status updates? If this lecture strengthened your architecture mindset, subscribe to the channel so you do not miss the next session. Like this video if you believe continuous evidence is the foundation of trustworthy artificial intelligence adoption, and comment below with your perspective. Is your organization building continuous artificial intelligence security monitoring, or is deployment still moving faster than operational assurance? Let us build secure, resilient, and continuously governed artificial intelligence systems together.